Picture this. It's 10:17 in the morning, and aircraft suddenly begin reporting impossible positions. Ships are appearing miles inland on monitors. Mobile networks start losing their synchronization, and financial systems can no longer agree precisely on when transactions actually happened. But here's the thing. Europe hasn't lost electricity, and the internet is totally fine. It has lost something most people mistake for just a simple map.
This right here is what a cascading infrastructure failure looks like. And no, this isn't some science fiction movie plot. These are the documented, real-world consequences of losing our global navigation satellite systems, or GNSS. We're talking about a scenario where automated workflows distort, data is compromised, and the modern world begins to slowly, inevitably grind to a complete halt.
But here is the central revelation of this explainer, and it's a big one. GPS does way more than just tell you where you are. It tells the modern world exactly what time it is. Officially, GNSS provides PNT, positioning, navigation, and timing services. It's that last one, timing, that is the ultimate secret. That invisible clock is quietly embedded in practically everything that makes modern human civilization function.
So let's dive into this. To truly grasp our sheer dependency on these signals, we really need to answer 3 critical questions today. What exactly would fail first if the signal drops? What would actually keep working? And is it possible that a device small enough to hide in the trunk of a car could disrupt infrastructure across an entire city? To answer those questions, we first got to understand the profound physical vulnerability of this entire setup. GNSS satellites are orbiting roughly 20,000 kilometers away out in space. By the time their signals reach us down here on Earth, they're incredibly weak. We're talking literally weaker than the ambient background radio noise of our own planet. And because these signals are so faint, they are highly susceptible to 2 forms of intentional interference, jamming and spoofing. The easiest way to think about it is like this. A genuine GNSS signal is a satellite whispering to us from space, while a local jammer is someone nearby shouting into a megaphone. Jamming overwhelms the receivers with sheer noise. It disrupts the signal completely and leaves you with a blank screen. Spoofing, on the other hand, is far more insidious because it relies on deceit. It transmits highly convincing false information. The real danger here is that your receiver completely trusts the fake data, calculating an incorrect position or time without raising a single red flag. Part 1, the countdown, when the map fails. So how does this actually play out? Let's walk through the ticking clock consequences of a massive location failure. In the very first minutes, the most visible layer of our tech fails. Smartphones can't lock onto a location, and car navigation systems become totally unreliable. You might see your car driving straight through a building on your screen. As we hit the early phase, aviation crews start receiving conflicting position data in the cockpit. Now, to be clear, planes aren't just going to fall out of the sky. Aviation has incredibly strict procedures and alternative ground-based navigation, but air traffic efficiency absolutely plummets, causing massive delays. By the mid-phase, maritime shipping vessels might pop up in completely false locations, entirely confusing traffic control in busy straits. In the late phase, port logistics just freeze up. Emergency dispatching gets chaotic because ambulances can't be perfectly routed, and automated delivery systems lose their pinpoint accuracy. But as disruptive as losing the map is, believe it or not, it's not the worst part.
Part 2, the unexpected failure, time.
Here is the true danger, the thing that turns a navigation headache into a full-blown economic crisis. Smart energy grids rely heavily on intelligent sensors called phasor measurement units. You can think of them as the grid's heartbeat monitors. They're constantly measuring voltage waveforms across vast distances to ensure power flows smoothly. But to do this, these sensors require time synchronization within a fraction of a microsecond. If the clocks drift beyond that minuscule margin, the system detects a false phase error. This can literally trick automated protection systems into needlessly tripping safety relays, which could easily cascade into severe power blackouts. And that exact same invisible clock, it powers the communication networks you use every single day. Modern 5G cellular networks require adjacent cell towers to maintain perfect phase alignment. If that synchronization drifts, signals overlap, data packet transmissions collide, and your calls just drop. But it goes way beyond phones. Massive data centers, television broadcast networks, and global internet routing protocols all rely on this synchronization to keep data perfectly ordered. Meanwhile, high-frequency financial platforms absolutely require incredibly precise timestamps to sequence millions of trades a second and prevent market fraud. So it all boils down to this tiny, tiny number, 1 microsecond. To put that into perspective, under the European Union's MiFID II regulations, financial operators are strictly mandated to prove their transaction timestamps trace back to universal coordinated time within a single microsecond. Without GNS, proving that compliance becomes remarkably difficult. It could potentially force massive trading platforms to suspend operations entirely until they can verify the exact sequence of their trades. Part 3. The growing European threat. And, this threat isn't theoretical anymore. In fact, on July 3, 2026, European aviation authorities updated their GNSS interference guidance precisely because this kind of interference is rapidly becoming routine. ESA, the European Union Aviation Safety Agency, alongside Eurocontrol, have had to roll out serious, coordinated mitigation plans. Between 2021 and 2024, reported GPS loss events increased sharply. What we're seeing now are spoofing bubbles frequently popping up around conflict regions and strategic infrastructure. There are real-world cases where multiple commercial vessels in the Baltic Sea or the Eastern Mediterranean are simultaneously reporting identically false positions. Figuring out exactly who is behind it is tricky. Interference can be intentional, it can be accidental, or just a byproduct of regional military systems. But regardless of the cause, the disruption is very real. To keep this all in perspective and avoid any over-the-top disaster hype, we really need to break down the threat scenarios logically. A local jamming event, say from a small device hidden in a car near an airport or a shipping port, creates a low, manageable impact. It's super annoying, but our systems can compensate. Regional interference, like those spoofing bubbles covering multiple countries or high-altitude flight corridors, elevates the impact to medium. That demands air traffic reroutes and fallback navigation. Finally, there's a system-wide global outage of all GNSS constellations. It is highly unlikely, but if it actually happened, the cascading infrastructure failure across our timing, power, and logistics networks would be absolutely catastrophic. Just how catastrophic are we talking? While a detailed study by the UK government estimated that a total GNSS outage would cost the United Kingdom's economy alone up to £1 billion per day. £1 billion. The financial stakes of this invisible utility hovering 20,000 kilometers above our heads are simply staggering. Part 4. Europe's defense strategy. But transport authorities and logistics operators aren't just sitting idle waiting for the lights to go out. We are actively building a really robust defense ecosystem. First up, Europe has its own navigation constellation called Galileo. The European Space Agency notes that Galileo's unique authentication service adds crucial cryptographic verification to navigation messages, directly helping receivers fight off spoofing attempts. Down on the ground, critical infrastructure is being equipped with backup atomic clocks. These independent timing systems can basically hold over and keep precise time even during an extended satellite outage. Aviation is heavily leaning back into secure ground-based navigation networks as a solid failsafe. Ships and commercial aircraft utilize self-contained inertial navigation systems that track movement without needing external signals. Flight and maritime crews are getting intensive training specifically designed to recognize spoofing anomalies early. And finally, there is a huge push and growing investment in sovereign, high-power ground-based positioning systems, like ELORAN, which are significantly harder to jam than those delicate signals coming from space. When you step back and look at it, GPS was originally built to just help us figure out where we are. But modern civilization quietly transformed it into something much, much larger. It's a universal clock for machines. The real danger of losing GNSS isn't that society instantly goes dark. It's that thousands of interconnected, automated systems, from 5G data towers to banking servers to electrical grids, would slowly lose their agreement about location, sequence, and most importantly, time. Which leaves us with this final, profound thought to consider. Our entire digital economy, the logistics that feed our cities, and the power that lights our homes all rely on a synchronized pulse beamed down from the vacuum of space. So, what happens when a civilization that relies on precision can no longer agree on what time it is? Can we really coordinate for long? While our vital timing signals travel down through space, the vast majority of our actual data travels under the ocean. Up next, we're diving into another massive hidden vulnerability. Check out our next explainer to see how cutting a handful of fiber optic undersea cables could instantly disconnect entire regions of the globe. You absolutely won't want to miss it.